Hey, hello there. Let's talk about today's Leetcoding challenge question. It is called reverse bits. So we have a 32 bits unsigned integer and we want to write a function to reverse the bits. So if we go about and write out the binary representation for 32 bits unsigned integer, the reverse of its bits, it's going to be as if we are reading the number from the right hand side towards left hand side. So that leads to a very simple solution, right? We're going to extract bit by bit from the right hand side towards left hand side and pipe those into a output so that the output would just be the reverse of this number. So let's code that up. It's going to be a loop based solution and we extracting this bit by bit. We run a loop for 32 times, extracted the i's position from the right hand side in each iteration and pipe that into some kind of a result holding variable. So we're gonna pipe this into this variable r. Initially it's 0. To extract the bit i's bit from the right hand side for this input number, we're gonna shift the number towards right by I. Then the very last bit is the bit that we want to extract. To extract it, we just do an AND operation with 1. So if it's 1, it's going to be 1. If it's 0, the end result will be 0. So we want to shift the output, temporary output towards left by 1 to make sure that we have a new place initialized to hold this newly extracted bit, and do an AND or OR operation to update that very last bit if it's necessary. We can change this to plus, it will be equivalent. So after this loop, we are pretty much done. We just return the output. So that's accepted. Let's talk about the follow-up very quickly. If the function is called many times, how would you optimize it? Looking at the code here, it's 32 times iteration, so it's pretty much a constant. If we want something that's better than constant, that means we want to memorize the result, and the next time we see the same number, we return that same number. So that leads us to think about to caching the result. Either use some kind of a hash map, or in this case, we can use the number as the index to grab the value stored in fixed size arrays. So that will speed things up if we see the number over and over again. The problem with that is 32-bit integers still have quite big range, so we won't necessarily see that many times of duplicates. So instead of caching the result for the full 32-bit number, we can chop it into individual pieces. The chance that we see repeatable chunks is going to be much higher than the chance we see the repeatable 32-bit integers. If the incoming number is, random, caching on the chunk is going to be more likely to be triggered in the end. So that leads to basically chop up the number into chunks and call some kind of a subroutine of this similar thing, but it's basically the same thing with memorization. If I know it, I return it. Otherwise, I will do this for loop to calculate and then memorize it. After that, we return the result. So the chunk size here, if the input is 32, I think it makes sense to try 8. So it will be reverse this number byte by byte, and then have to piece them all together. So the code in this function is going to be dealing with the chopping and the piecing together, and also the function call. We're going to basically make a copy of this and make that into a smaller function to only work on the chunks. We call this now reverse byte. It's going to be, the input is going to be a single byte number we pretty much do the same thing, but only on 8 positions now. We have to somehow incorporate the memorization there. So I'm gonna use a vector here. The idea is we want something that can be accessed by index. So we can use the number as the index so that we can directly look up if we have the result cached there. So we have to initialize this here. It's going to cover the single byte range, so it's 2 to the power of 8, that is 256. Initially everything has to be 0, can be 0, so when we see 0 we know we haven't calculated the number yet. So if not, mapping n, and also the number is really indeed we need to calculate that, because the reverse of 0 is just 0. So this condition is telling us we do have to do this calculation. Then we do this calculation and memorize the result. So that converts the original reverse bits into reverse bytes. Reverse byte. So it's a 8-bit chunk of the input. So the math logic here is going to be the divide and conquer thing. So what we're gonna do is to first pass the rightmost 8 bits single byte, extract those and pass that into this reverse byte. And after we've done that reverse, we have to shift that towards left by 24 to make them the leftmost 8 bits. So to extract the rightmost 8 bits, we can do an AND operation with this. This bit mask. So this AND operation would extract the rightmost 8 bits. Once we've done that, we pass that into the reverse, and then shift this towards left by 24. So that the reverse of the rightmost 8 becomes the output, the leftmost 8 bits in the output. And we just do this for 4 different chunks. Obviously we can with some logic to wrap this thing into a loop, but since we're dealing with 32, I think that this is fine. If this is arbitrary, then the chunking can be more organized using variable to handle the shifting size, and might be a loop to do this instead of 4 different lines. But here I'm just want something really quick. So the second group is the 9s towards 16s from the right hand side. To obtain this 8 bits, we're going to shift the number towards right by 8. So destroy the rightmost 8 bit, and then grab the next 8 bits. Do a reverse of that, and then shift this towards left by 16. So this is 8, and this is pretty much 0. Here we're shifting towards right by 16. This is shifting towards right by 24. If we really have to make it more obvious how we want to convert this, how we can convert this in loop, we do this. So after this, the output should be the desired output. Let's see if it works. Okay, it works. So this works as well. So here we're still building on top of this one, the reverse bytes. It's essentially the original solution to this problem, but only work on smaller size. And the reverse bits is the divide and conquer logic. It's chopping the problem into smaller problems, look it up, and try to piece them together, piece them up together. So that's one of the possibility for the follow-ups. Obviously here you only have 256. You can pre-calculate that. Here is just do the caching on the run, on the go. Otherwise you can pre-calculate 256 and just put that into the constructor. You would do too. So that's pretty much the solution to the original question, and also one of the possible answer to the follow-ups. I guess it's to realize we can do some kind of a divide and conquer is that the chance we're gonna see the same 32-bit number over and over is gonna be low, but the chance we see the chunk of it, it's gonna be potentially higher. So that can trigger the idea of doing this. Last thing that I want to talk about is the solution, one of the solution here. So this thing, I don't think interviewers are gonna expecting to see this. So I don't even want to talk about that. Let's talk about this very last solution here. It's doing something very when you first saw it, it might look like some black magic, but the idea is pretty simple. So I'm going to demonstrate that. So it's doing reverse by swapping. If I have a string, something like a 1, 2, 3, 4, 5, 6, 7, 8. If I want to reverse it, I can do first to swap the adjacent pairs. So it will be 2, 1, 4, 3, 6, 5, 8, 7. And the next thing, we can swap the adjacent pair of size 2. So it will be 4, 3, 2, 1, 8, 7, and 6, 5. Last step, we're gonna swap the adjacent pair of size 4. It will be 8, 7, 6, 5, 4, 3, 2, 1. So with this swaps of adjacent pairs, when the size is going from 1, 2, 4, 8, 16, if we do this swap twice the size every time, the end result will be equivalent of reverse the whole thing. So this code, it's essentially that, but using bit mask. If we look at this here, the mask here, F, this one, A, that is to, I think that is just 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. So it's effectively grabbing the even or odd position bits. This one is one short of that. So anyway, this basically is to grab even, grab odd, and do a shift and operating them together. So this line is effectively making 1, 2, 3, 4 to 2, 1, 4, 3, 6, 5, 8, 7. So it looks miraculously, but the idea is just doing this reverse by swapping pairs with the size incremental by 2, factor of 2. It is just it's expressed as bit manipulation. So this one works too, but I don't know if interviewers are gonna really expecting this. But if you have difficulty understand it, just think about this example. You will figure it out. So that's the question today.